Okay, thank you very much, and thank you to Renzo for again organizing this fantastic workshop and for inviting me. So I'm actually going to return to something that Mitch Berger was talking about, one of his topics on the very first day, and spend some more time going in detail. This wasn't planned in advance, but that's how it turns out. And I'm afraid to say, of course, we're going back to magnetic helicity yet again, but an interesting topic. So my motivation comes from solar physics. This is how I originally got interested in magnetic helicity. And I was, or still am, particularly interested in modeling the magnetic field in the sun's atmosphere. So this is an image during a photograph during a total solar eclipse. And what this allows you to do is see the structure of what we call the corona, the kind of atmosphere of the sun, essentially. And you can see all of this structure from scattered light, but it's illustrating the shape of the magnetic field. And what you don't see in this picture is that the structure of this magnetic field is quite dynamic. It's changing. And in fact, you see a signature of this. If you look over here, I don't know how well you can see it, but there's kind of a bubble here. This is moving out of the sun, and we know that this is actually a tangled bundle of magnetic field that has erupted suddenly from where it's been sitting in the solar atmosphere and thrown out in what we call a coronal mass ejection. Another thing you can actually see in this image, if you know where to look, is this little dot down here. And this is a comet that happened to be going past at the same time. And apparently it was discovered by an amateur scientist. So this is a model of the magnetic field in the corona. But there's kind of two, I think the way I see it, there's two possible applications, if you like, of magnetic helicity in this kind of area, practical applications. The first one is predicting these eruptions. So I don't know if I can play this again, just for. There we are. So you see that as the sun evolves, it kind of stresses this magnetic field in the atmosphere, and you build up these tangled bundles, and then suddenly they erupt, like we saw in the eclipse. And so helicity is potentially a measure of this sort of tangling of these bundles of field. And so you can imagine that if you look for places where you've got helicity in the corona, you might be able to say something about where you're going to get eruptions. The second motivation is a sort of a more, I don't know about philosophical one, but a more a less direct application, and that is to think about the sort of picture of helicity transport. So for a long time in solar physics, there's been this general idea that magnetic helicity is somehow injected into the atmosphere by things coming out of the sun. It's somehow stored in the atmosphere in these twisted bundles, and then every so often it gets ejected. And so it would be nice if you could actually quantify this process. And to do that, you need to be able to calculate the helicity. And to do that, you have to be able to define it.
Excuse me, Ant.
Yes.
Just a question. So the difference between the blue and the white lines is just what?
So it's actually showing you the field line helicity that we've heard about a couple of times. I don't think we really need to know that for this talk, but it's basically the helicity in a thin tube around each field line. We might get to this again at the end, depending on the time. So just to remind you, where does helicity come from? Well, this is the MHD induction equation that we've seen multiple times this morning. And that's the basic equation that governs the magnetic field evolution. And so the idea with helicity is that if you uncurl this equation, so you write your magnetic field as the curl of a vector potential, then you get some equation for that vector potential. Because you uncurled, you've got an unknown gradient function. But if you look at the evolution of A dot B, then you can see it satisfies a conservation law. So, the d by dt of A dot B is the divergence of something. And so if you integrate over some volume, then you get the rate of change of the integral of A dot B is a boundary term. Right? And this integral of A dot B, of course, is the magnetic helicity that we keep hearing about. So something you can notice, so the magnetic helicity is not gauge independent in general because of this boundary term, because you see in this boundary term, it depends on the phi here, which was basically the gauge. Another way of looking at this is if you change A to A prime by adding the gradient of some chi, then your helicity, if you just plug that into the definition, you see that it becomes again a boundary term. And so the effect of a gauge transformation is just the same thing as doing an ideal evolution in some sense. So that's important. So, oh yes, so you can get rid of this extra term if you don't have a boundary. So, you know, if you have the helicity of all of space and you have some physical magnetic field that tends to zero fast enough as you go to infinity, then this boundary term goes away. And in that case, the magnetic helicity is not only a gauge invariant, but it's also time invariant, assuming you have this ideal evolution. So that was a sort of introduction. The question that I want to address in this talk, I'm not sure I'm going to completely answer it to everyone's satisfaction, but my best thinking on it so far is how do we define the helicity in our sun case, right? So it's basically a spherical shell. So the region between the sun in the middle and some surface on the outside where my calculation stops, if you like, or where our observation stops. And of course, because this is, we saw in the real sun, the magnetic field lines kind of come out of the sun and head out of the top. So you don't have this tangential condition on these boundaries. And so the helicity is gauge dependent, and it changes according to this boundary integral. So the question is, how do we choose which gauge to use? So it's actually, I think, useful to first of all think about the case that we understand, which is when we have the whole of space and it's nicely conserved, and think a bit more about what the helicity means in this case. And we've kind of heard this before, but I think it's worth going through again. So I couldn't find a picture of some infinite of pasta, but this is you have to imagine you have some magnetic field sort of filling space, and it decays sufficiently fast as you go to infinity here. So probably everyone now knows this. You have this interpretation of the helicity as a linking or a net linking between magnetic flux. So, and you remember the way or a way to prove that is to think about the Coulomb gauge. So the well-known formula from electromagnetism, your vector potential can be written as this kind of Biot-Savart integral here. And if you plug that into the helicity, the integral of A dot B, you get some formula here. For the helicity purely in terms of the magnetic field, so it's manifestly gauge invariant. We're assuming here that we're talking about the whole of space, so there's no boundary. And why does this correspond to linking? Well, it's basically the Gauss linking number somehow in disguise here. Go through this reasonably quickly. If you had, for example, a family of kind of closed magnetic flux tubes without any twist, then you could basically rewrite the helicity as a sum over those tubes of the flux times this remaining integral, which is precisely the Gauss linking number. So I think we've seen this more than once already this week. Now you can look at the Coulomb gauge in another way, which I think is several other ways, but you can look at it in terms of the Helmholtz decomposition. So, you know, if you have any well-behaved vector field, you can uniquely decompose it as something that's divergence-free and something that's curl-free on R3. And it's actually also an orthogonal decomposition. I don't think we're going to use that fact. So how do you see, what does this have to do with the Coulomb gauge? Well, you can actually just rewrite the formula. So that R over R cubed is basically minus the gradient of 1 over R. And because this gradient is with respect to x here, not x primed, you can take it out of the integral, and then you see that A is basically the curl of something. And so the Coulomb gauge, so it's divergence free, and it's equivalent to choosing a gauge where U equals 0 in this general representation. So in that sense, it's the kind of the simplest choice of gauge, if you like. Simplest choice of vector potential. And there's an even, I think, a nicer way that you could say, well, what does simplest mean? Well, maybe you minimize some aspect of A, and if you just minimize the kind of 2 norm of A, integral of A squared, turns over all possible A's that give you, match a given B when you curl them, then you actually get the Coulomb gauge. So you think of any other gauge would have to be the Coulomb gauge plus a gradient. And so if you plug that in, you get the norm of the Coulomb gauge, norm of the gradient, and then a cross term. And because the Coulomb gauge has this property of being divergence free, you can write the cross term as a total derivative. And so because we've not got a boundary, as long as we have these things finite at the boundary, then this term will go away. And you can see that the way to minimize this whole integral, the only thing you can change is this U, so you choose U to be constant, or equivalently 0. So the point is that in this case of the whole of space, you have this nice vector potential, and it gives the helicity, or it shows you that the helicity has a nice topological interpretation. So I'm going to try and recover as many of these sort of properties as possible in our case where we don't have closed boundaries, where we have a finite spherical shell. But before I move to a spherical shell, we're going to do the easier case of what I'm calling here a slab. So this is basically the region between 2 parallel planes. And again, we saw this in Mitch's talk a bit, but I will remind you. So this would be like here a lasagna, but the parallel planes are the layers of pasta here. So I'm going to call these parallel planes, I think, SZ, S sub Z in this talk. And here in red, these are my magnetic field lines, and you can see that they go out of the boundary at the top and bottom in general. So that's the setup for this part. So what does this have to do with the sun? Well, one thing is that we often model, as Gunnar showed us very nicely, we often model in solar physics these sort of coronal loops, as we call them, with magnetic flux tubes that connect to the sun at both ends. We often model them by a kind of simpler geometry where it's just Cartesian and they connect between the 2 planes. And so there are sort of direct applications of this as well, but it, I think, gives us a good idea of what we should be thinking about in this spherical case. So now, I think Chris mentioned this yesterday, but I'm going to say a little bit more detail. What gauge do we choose in this case, this slab domain? So you think, oh, well, let's just use the Coulomb gauge. And the problem with the Coulomb gauge is that in this domain, when you take the curl of it, you don't get B anymore. You get B plus a boundary term. Okay, so if the magnetic field was just closed within the domain, it would be fine. But when you have a B normal on the top or the bottom boundary, it doesn't close up nicely. But there is a way out of this, which is to have a sort of 2D version of the Coulomb gauge. And this is what Chris and I called the winding gauge. It's also a sort of Biot-Savart integral. I'm going to call it AW so that we can identify it here. But now the integral is only over a single surface a single one of these sort of leaves of the foliation. So if I want to calculate my my vector potential here, I only integrate on the SZ, the gray surface. And so my R, like the distance between the point X and the point X primed, is only a sort of a two-dimensional vector, essentially. So you can show that if you curl this thing, you get B now. I'm not going to go through the proof of this. You can also show, and Chris had some examples like this, where it works also for a finite domain. So I've sort of not talked about the side boundary, but if you have like a cylinder or something that has, it's between two planes, but it's only a finite region, then as long as you have no magnetic field going out of the side, this construction still works. You can still curl this integral to get B. What I want to say a little bit about is its interpretation, because that's a sort of important thing here, I guess. So whereas the Coulomb gauge had this interpretation, or it gave the helicity this interpretation of Gauss linking, what's going to happen in this gauge is that you get the interpretation of we call winding, which again we have seen, but let me just mention this again here. So what's the winding number? So the winding number is basically a topological invariant if you have two curves that have fixed endpoints, the blue and the red curve here, and you look at the angle between them in a horizontal plane, that's this theta. So it's the angle between them with respect to some fixed direction, the x-axis or whatever. And this is the angle theta. Theta will change as they move up in height here through this domain. And if you calculate the net rotation, you get this thing called the winding number. Okay, you normalize it by 2 pi to get a sort of integer number of, well, it would be an integer number of rotations if the curves came back to the same place. In general, they're not going to come back to the same place, so it'll just be a real number here. Now, if you do some algebra, you can rewrite this in a more complicated looking form in terms of this R perp, the distance between X and X primed. And that's going to allow us to relate it to the helicity. In the winding gauge, you plug in your 2D Biot-Savart formula, and you get some expression, and you can rewrite this expression if you think of B as being BZ plus B horizontal, and you do that for both the copies of B, then you get an expression something like this. And basically, the upshot is you rewrite your helicity in the same form as the winding integral here. The only difference is that where you had dx by dz, you now have B horizontal divided by BZ. And so that means that it's the winding between the magnetic field lines, because a magnetic field line is an integral curve of B is precisely defined by the fact that dx by dz is Bs over Bz. So if you want to think of a discrete collection of tubes like we did for the helicity, then your helicity in this gauge is just the flux-weighted average of this winding number, this pairwise winding number. Okay, so it has a nice topological, physical, if you like, interpretation. And you can see immediately from that it's going to be invariant if you fix the endpoints, because you can't change these winding angles. Okay. Oh, I had some examples here. So now this, I think it's just interesting to see some concrete examples. Let's just, there's not very many cases where we've succeeded in sort of analytically evaluating this Biot-Savart integral, but one case where you can do it is if your magnetic field is sort of cylindrically symmetric. So you have, let's say, for simplicity, just a uniform field in the vertical direction and then some sort of twisting component. And you can show you can actually do the integral and arrive at this nice simple vector potential. for this case, and so you can get an expression for the helicity. An interesting thing that comes here is that if you look at what would this f have to be in order for this helicity integral or the integrand to vanish, you actually get a kind of non-trivial, even in this axisymmetric case, you get a non-trivial kind of kernel of this thing. So in other words, you get solutions that have zero helicity if they satisfy this ODE here, and the solutions of this ODE would be basically an arbitrary constant times r squared. So B was the derivative, or B phi was the derivative of F, so that would be a uniformly twisted magnetic field, if you like. So this seems a bit odd. How does this uniformly twisted field, by our definition, has zero helicity? But that's because the helicity is like the internal linking. It's the linking between pairs of field lines, and they don't have any net linking if they're uniformly twisted. So this is not completely crazy. I mean, this field would be a bit, if this just extended to infinity, it would be sort of unphysical. You'd be more likely to have something like this, where the twisting is localized. And in that case, you do get a helicity. There is a net twist between the field lines, and just turns out to be some expression if I take the limit to infinity, basically just proportional to the k, proportional to the twist here. So you can have these fields that where you can write down the helicity. So some more examples that are going to be numerical here. So solar physicists are often interested in these what we call potential fields or current-free fields where it's curl-free. As we heard, I think Gunnar was discussing, these would be minimum energy states in sort of MHD. And turns out that these can have non-zero helicity. For example, if you have a domain where you have different boundary conditions at the top and the bottom, you can force the current free field to have a twist, if you like, or some topological structure. This plot here is just showing you the sort of density of helicity on a cross section of this field, and when you integrate it, you get a non-zero value. This thing has a negative twist. So you can get it can pick up winding that's kind of somehow coming from the boundary conditions. You can actually apply this, although this is no longer a slab domain as such, but you can apply it to kind of more complicated shapes of domain. And in this domain, the boundary conditions are uniform, but you pick up a winding because the whole domain is wound. So you could sort of think of it like this is a kind of writhe helicity, and this one was a twist, I guess, or the previous slide was a twist. But anyway, so you can, in these more general domains, you pick up this topology. Okay, so for the Coulomb gauge, we had a nice kind of interpretation in terms of this, I don't know, a kind of variational interpretation. It was like minimizing this integral of a squared, or it was sort of taking only part of the Helmholtz decomposition. And you can do a similar thing with the winding gauge. So turns out that if you have a vector field, so a three-dimensional vector field, but it lives on a two-dimensional surface, and this surface is simply connected, and it has a normal vector n hat here, then you can, the sort of appropriate Helmholtz decomposition is basically some part that is sort of the equivalent of the tangential curl, if you like, of this in-plane curl, and then a gradient in the plane. So the S here always means in the surface, and then the component normal to the surface. And the winding gauge turns out corresponds to this. Well, firstly, it corresponds, sorry, to this setting u equals 0 here. So why is that? Well, it's analogous to the Coulomb gauge. You can rewrite it as the curl. This time you've got your curl is a sort of surface curl, as it were. So so it has the property that the surface divergence vanishes. Right? So the Coulomb gauge had the 3D divergence vanished. The winding gauge has the surface divergence vanishes. And analogous to the Coulomb gauge, if you like, it minimizes the norm squared, but of only the horizontal component of A on every leaf of the foliation, every slice. And so it's another way it sort of maintains these properties as well. And I should mention, relating back to Mitch's talk, from this fact that we got rid of this gradient term, you can immediately see that this, for the case of our slab where the surface is a plane, n hat is Ez, so it has no curl, you can write it in the poloidal-toroidal form that Mitch showed us earlier. Okay, so we're talking exactly about the same gauge, in fact, as it was proposed by Mitch. You have to be a little bit careful, because the winding gauge corresponds to a particular choice of T. And this representation is not unique. You can add a function of Z to T without changing the magnetic field. But the winding gauge is a particular one. Okay, so I think I should move on to what I was really interested in, which is spherical shells. I couldn't find any pasta in the shape of a spherical shell, so this is the best I could come up with. And hopefully I'm not holding you back from your lunch for too long here, but this is again a reminder of the domain. It goes between R0 and R1. And what can we do here? So it's kind of like the case with two parallel planes, but now it's two somehow concentric spheres. And there's something nice that happens here, because although the boundary has two components, both of them are closed surfaces. And because of that, it turns out that you can uniquely define the helicity just by imposing this horizontal divergence to vanish on the boundary surfaces. So in the plane case, we had to also impose that it vanished on every surface going up through the domain, but here it's enough to impose it on the boundary. So we have time, let's have a look at this. So let's suppose we have two different vector potentials A and A prime that both have no divergence on either boundary. So they differ by a gauge function. And so this gauge function, this chi, has to satisfy the sort of two-dimensional Laplace equation on both boundaries. And so follows that it has to be a constant on each boundary, the only possible solution of the Laplace equation on a sphere. But the two constants could be different, right? We haven't imposed a relation between the constants. So there's still some gauge freedom, if you like, here. So let's we calculate the new helicity, H primed, and remember it was the old one plus the boundary integral of the gauge function times Bn. So now the gauge function is chi1 on the top boundary and chi0 on the bottom. But not only that, the flux, if you like, the integral of Br over a sphere vanishes because B is a divergence-free field. So I'm assuming that it's also divergence-free inside the sun here in making this statement, which is presumably true in any real application. And so if that's the case, the two fluxes are the same, and so your helicity, you can combine them. These two things were constants, and not only are the two fluxes the same, but they're zero. So this integral here vanishes. If I actually wrote that on the slide, but so this helicity, in other words, is invariant. So it's enough to specify this condition on the two boundaries. The horizontal divergence of A equals 0. So my kind of proposition, if you like, is that the best choice of gauge, or the best choice of helicity in this domain, is to impose this condition. And I'm going to call the corresponding vector potential A star. and the corresponding helicity H star on the sort of indicating that it's the best one somehow. So we have the poloidal-toroidal decomposition in spherical coordinates, because and so you can write A star as the curl of a potential plus another potential in the R direction. So the way you would actually find these potentials is to solve two Poisson equations. So you're given what the magnetic field B is, the P potential has to have its Laplacian equal to minus BR, and the T potential has to have its Laplacian equal to minus the R component of curl B, which is the current JR, we normally would call it in MHD. And now you can't solve these equations in general. You need a kind of compatibility condition because you've got a closed surface. It's kind of periodic domain. But the compatibility condition is just that for the first equation, you need there to be no flux through the sphere, which we already saw as the kind of follows from the fact that div B equals 0. And then we also need there to be no current through this, no net current through the sphere, which again will be true in any physical case. And if we do that, we can solve them. So the solution's only defined up to like an additive constant for each potential, but one, you can do it with a Green's function, as I have here. And the Green's function in the spherical case is this log of 1 minus cos psi, essentially. Now psi here is just the spherical distance between x and x primed. So I didn't write down the expression in the Cartesian case, but the analogous one there would basically just be log r, something like that. Now we have this log of 1 minus cos psi. But anyway, this gives you an explicit formula for this this vector potential if you then calculate this through. So you can compute it. Now, remember the P and T are defined only up to an additive constant. The constant in P doesn't have any effect because already in the vector potential it's curled out. So I say an additive constant. It's an additive constant in each surface. So it's a function of R essentially. But that function of R curls out in P. But T, the extra function of R, down here, if you add an extra function of R, you do change the vector potential. But as we saw, you don't change the helicity, total helicity. Okay. So a nice property that this thing has is a sort of additivity. So additivity when you consider sort of concentric shells. So if I divide up my domain into two concentric shells, VA and VB, then I have that H star of the whole domain is just the sum of the two. And this just follows because everything is just defined by integrating over individual spheres. So you can just add them up. But that's actually quite an important property because, for example, it allows you to make a kind of meaningful definition of helicity flux from one layer in the atmosphere to another. So I have an example of this, which maybe I need to explain a little bit. So this is a super sort of toy model of what's happening in the sun's atmosphere. I'll play it again in a second. But what we're looking at here, so we've obviously got, here's the sun, this is the magnetic field. On the surface of the sun, I don't know if I can actually control this here, perhaps. Let's see. Okay, this is the initial condition here. So on the surface of the sun, you're looking at the contours of the radial magnetic field. So white is where it's coming out and black is where it's going in. So you see the loops coming around. And I've got some pattern here. And what's happening in the evolution is that first of all, I put the sort of first property of the sun, which is that it rotates. So it rotates actually differentially. So the equator rotates faster than the poles. So you get a kind of shear flow on the surface of the sun. And that's going to be injecting helicity in some sense into the atmosphere. But on top of that, you have Gunnar, I think, described the small-scale turbulence on the surface. And I'm modeling that small-scale turbulence in an incredibly simplified way as a diffusion, a surface diffusion. So where I have a positive and a negative magnetic field, over time, they're going to basically cancel each other out. So that's what's happening in the simulation. Can I play it again here? Perhaps not. Right, there we are. So so what's happening is, so again, the field lines are basically colored by their sort of helicity density, the integral of A dot B along that particular field line. And it's a bit quick here. So you see that the helicity is being injected. You're forming one of these twisted bundles, and then it's a bit fast, but that bundle is suddenly disappearing. So you form the twisted bundle because of the flux cancellation. So the differential rotation is shearing it. That's giving you the field component out of the board. Then the cancellation is cancelling the vertical component, the radial component, but leaving behind the horizontal field. And so that horizontal field ends up in these kind of twisted bundles. Now, on the right, we don't need to look at all these graphs, but the middle one is showing you the helicity in each hemisphere, total integrated. And you see in the northern hemisphere here, it's increasing during the experiment. The whole axis here is 70 days, by the way, or something, 75 days. And on a sort of day 70 or something, suddenly the helicity drops in the northern hemisphere. And that's the time where the flux rope is got so much, it's become so strong that it's no longer stable and it gets ejected. Now, I was talking about the helicity flux. So what you can do, I won't bore you with the equations, but you can calculate the flux of this helicity into the domain at the bottom and out at the top. And if you calculate the flux in at the bottom, I think I'm doing this in a single hemisphere here. The flux in at the bottom is this black curve here. It's not actually a straight line. It's slightly decreasing, and that's because of we're slightly weakening the field by this diffusion over time, but at a slow rate. But there's a constant helicity flux in at the bottom, just coming from the fact that the sun is continuously shearing the field. But what's interesting is that the flux out at the top, which is the blue dashed line, is gradually increasing, but then it has this sudden jump. And that sudden jump is when the flux rope is ejected. So it's almost like the sun's atmosphere somehow processes this constant input of helicity and then sends it out into the solar system as a combination of a sort of steady rate and every so often a massive burst in these eruptions. So it's kind of an interesting evolution. Okay, so something else I should mention, there's another way of looking at this helicity, this H star, and that is that it's the helicity of a magnetic field on the whole of space if you extend your magnetic field in your spherical shell by a current-free field, so by a potential field, or in other words, a B that's a gradient of something. So here I've had to extend it both inside the sun and outside, right, to fill the whole of R3. And why is that the same? Why is the helicity of this whole thing the same as just our original helicity? Well, it precisely comes from the fact that if you have a current-free field, it has, on any of our spherical shell, or any spherical shell, it has no H star of its own. And you just see that by the fact that a current-free field has a vector potential here with no T term, if you like, because the T term came from a Poisson equation with the current. But if you have no current, you have no T. So, okay, and then you integrate that over each shell, and you find that it vanishes. So you know, if you want to, you can think of we can define the helicity of this finite domain with an open boundary as the helicity of some total field over the whole of R3, where outside our domain, that field is simple. And this is equivalent in this case to the relative magnetic helicity that we've heard about a couple of times. I think I don't need to actually define it and go into detail. But the idea of extending the field is the key thing. Now, you could say that this extension isn't very realistic because there's no way that inside the sun there's no electric current in real life. Nor is it true that there's no electric current outside the inner corona. But somehow by assuming that there's no current, we're isolating only the topology of the field within our region, in some sense. So that's sort of an alternative way of looking at it that also makes us think that this is probably a good definition of the helicity. Okay, so this is going now, I think this is pretty much the last thing I want to discuss, going back to Renzo's question about what will the colors mean in these plots. This is when I try and calculate the helicity of a sort of subdomain. So in that case, I was coloring in the individual field lines, but you could have some larger subdomain if you wanted. So I'm going to, let's say U is some subdomain of V, and I'm going to make this assumption that it's what I would call a magnetic subdomain. So what that basically means is that it's kind of a bundle of magnetic field lines. So there's no interior boundaries where the magnetic field goes through. So for example, you could have these red field lines that connect from the inside sphere to the outer one, a sort of bundle of those. They don't go through this side boundary here. Or you could have some field lines that connect between the inner sphere and back to the inner sphere. Or you could have them connecting from the outer sphere back to the outer sphere, but that's not so common in solar physics. Just the same. And so there is a sort of a slightly interesting thing here, is that if you have, I talked about this arbitrary choice of T. So if we just impose this condition that the horizontal divergence is 0 on the boundaries, or equivalent, we use a poloidal-toroidal representation, then we have still this arbitrary choice of T up to a function of R. And turns out that the helicity, well, when your field lines only connect to one boundary, you don't see this because they all have sort of the same constant on them and it cancels out. You see it when you have field lines that connect between the boundaries. So that's something that unfortunately happens here. Oh yeah, so this is what I was saying, the field line helicity. If you take these, you can see that the finest possible decomposition you could make would be to have some infinitesimally thin tube around every single magnetic field line. And all of those tubes would satisfy my condition of being magnetic subdomains. Now, if you have an infinitesimally thin tube, you have to sort of normalize the helicity as you take the limit. So I normalize by the flux of the tube, essentially. And then you get this quantity that was actually introduced, I think, for the first time by Mitch Berger in the 1980s, certainly in the solar physics context. And then not many people did much with it for quite a long time, but I guess because it's slightly more difficult to compute. But seems like the sensible thing to look at, if you don't a priori know how to divide your domain into subregions, you look at the finest possible decomposition. So this is just to give you an example of the kind of thing you can do with this. This is a simulation that looked at with a former postdoc, Chris Lauder, and I basically gave him the task of trying to identify these magnetic flux ropes, as we call them, the sort of bundles of twisted field in the atmosphere during this simulation by using this sort of a threshold of field line helicity. So places where this field line helicity is above some arbitrary threshold. It's in spherical geometry. I've just flattened the whole sun out into a rectangle here. And the time is going incredibly fast. This simulation covers like 11 years of real evolution, or even more, I think, 15 years. And so you see the sun's differential rotation is happening really fast. The black contours are showing you the contours of the magnetic field on the sun's surface, sort of orientation. So you see that their new bits are emerging, they're being sheared by this differential rotation, and eventually they're disappearing by the flux cancellation. And then you get some complicated magnetic field in the corona above. And we've colored in, field lines that have very strong helicity, essentially. And you can see that they end up in these tight, twisted bundles. So what Chris did was just, well, several things, but one thing was just calculate how much helicity is in these things and how much of it is ejected into the solar system, as it were, in the model. And you get some rate of helicity ejection per day. It varies over the solar cycle, of course, because you have, when the sun's more active, you've got more energy and more magnetic field, or magnetic flux. And but if you calculate the integral over the whole cycle, you get some number, which is probably meaningless to most people here. But the important thing about this number is it's actually quite close to the estimates we have physically of this, which are based on basically satellite observations near to the Earth. So you wait for these ejections to come past us, which of course doesn't very often happen. Well, happens reasonably often, but most of them head off in some other direction. But you measure the ones that come past us, and by some sort of very rough fitting, you try and estimate how much helicity they have. You only have a single point of observation, so you can't really see what exactly the structure is, but you make some estimate. And when they do all of that, they get a similar figure for the amount of helicity being ejected in these eruptions. So that's quite nice. Okay, this is just a quick remark. So when we were looking at the parallel planes, the slab domains, I showed you some examples of potential fields, current-free fields that had non-zero helicity. Now, I just told you that in the spherical case, potential fields have zero helicity in our definition. But if you look at the field line helicity, then that's not zero, because we had to integrate over the whole sphere to make the helicity vanish. So this is just an example of a time on the real sun, I think it was in 2014 or something like that, where I've just extrapolated a potential magnetic field from the observations of the real kind of boundary, the solar surface. And I chose this particular time to illustrate here because this is the time that had the most helicity, or the most field line helicity at any time over the solar cycle 24. And it turns out that it all comes from this enormous active region. It's got a huge amount of magnetic flux. And the helicity, it's not really a self-helicity of the region. The region's not, well, in my potential model, the region has a very simple structure, but this region is linked with the overlying magnetic field that kind of goes from the high latitude, imagine like a sort of dipole. And this linking, and its flux is so strong that this linking gives you a large contribution of field line helicity in that region. And this is in the minimum energy configuration. So even if you only look at the minimum energy configurations at different times, you can still say something about the topology of the field by looking at in particular, the field line helicity. Okay, so one more slide here before we get to the conclusion. Now, this is a slide about ongoing work. So Chris and I have a PhD student, Daning Zhao, who is interested in helicity and this kind of thing. And so we gave him the task of answering the sort of outstanding question that I haven't yet mentioned. And that is, what is the sort of physical interpretation, or can we make a physical interpretation of this H star in terms of winding? Because that was somehow our original motivation for looking at the Coulomb gauge, looking at the winding gauge. And so we saw that probably this is the right choice because it has these other properties, but can we go back and say, what does it mean in terms of winding? So the short answer is I can't yet tell you, certainly not in the time we have available, But it looks promising that we are going to be able to get some nice formulae coming out here. So basically, what do we define to be the winding angle in order to recover this helicity? So this is just a movie at the end here that Chris made. It's this Dirac belt trick, which we heard about in Mitch's talk, and this idea that winding is a bit of a slippery thing in spherical geometry or in this spherical shell, because you can change the sort of winding angle between two curves by moving it around the other side of the sphere. So the endpoints are fixed here, but we're doing an isotopy, but we're somehow changing the winding from we're changing it from sort of 0 to 2 pi or something. And you remember this. I don't think this is going to be a problem for the helicity, because the helicity you've got to average over all of the other curves in the field. And as Mitch mentioned, I think if you fill up the field with other curves, you see that when you do this maneuver, you induce a twist in the surrounding curves. So it's like a framing. You've got to take into account the framing of these curves. But it poses us a little bit of a problem for how we define the individual winding numbers. So this is something we're working on, and I think it'll be hopefully a fruitful thing to look at. Fingers crossed, as Chris is saying. So okay, so I may as well finish at this point. So what do I say here? Let's see. So hopefully I've shown you that in magnetically open domains, magnetic helicity, although it's not uniquely defined, there's good reasons for defining it in a particular way, making a particular choice. And the nice thing is that several of these sort of possible ways of choosing it seem to converge, if you like, give you the same answer, at least in the domains that we've considered here. So, you can think about field line winding, you can think about the poloidal-toroidal decomposition, you can think about minimizing the 2 norm of the vector potential, and you can think about the relative helicity. And so I think we're on reasonably safe ground in using this definition in applications. But as I say, it would be nice to complete the sort of loop and know what the winding actually means in spherical geometry. So I'll stop there. Thank you.